Assalamu alaikum. We meet again for operating systems CS317. This is lecture 7. We start a new chapter today named Threads, and I am going to refer to chapter 4 of the William Stallings book for this topic. Up till now, we've just talked about processes. We had a full chapter that covered every aspect of processes. Now we're going to move towards a new topic, and that's threads. So the first question is, what is a thread? The second is, how is it different from the process? And an obvious question that springs from these questions is that why do I need to talk about a thread, or why do I need to know about a thread when I already know processes? If the operating system allocates memory, who does it allocate it to? A process. If the operating system allocates an I/O device, who does it allocate it to? A process. If the operating system allocates a file for reading or writing, who does it allocate it to? A process again, you say? Remember, I said the operating system is the god of the system. The god of the system bestows resources like memory, files, I/O. But who does the god give these blessings to? A process is the receiver of these blessings. No doubt the OS gives them out, but if you are not a process, the OS will not give them to you. In order to receive resources from the OS, you must be a process. When a program is translated into a process, it is allocated space in the virtual memory. What is this allocated memory called? The process address space. Well done. Everything that is kept in the process address space constitutes the process image. The process image has four main parts. Can you name them? Program, data, stack, and PCB. Correct. Now, when the OS blesses a process with a resource, it places the pointer to that resource in the address space of the process. A pointer is an address. Specifically, this pointer to the resource is written in the PCB of the process. The permission to use the resource is also granted by the OS and noted in the PCB of the process. If you remember, I told you that a process can only read or write in its own address space. It cannot read or write the system address space or the memory locations of the OS. It cannot read or write in another process's address space. So, when it gets a pointer to a resource in its own address space, it can read this pointer and it can use this pointer to access the resource. This pointer is called a handle. A file handle is pointer to a file. An I/O handle is pointer to an I/O device. A memory handle is pointer to a block of memory outside the process address space. This has been a long explanation. Let me sum up all that I have said so far in one sentence. The process is the unit of resource ownership. If the operating system assigns the processor, who does it assign it to? A process. We saw that the dispatcher picks someone from the ready queue according to the scheduling algo it follows and gives the processor to it. So this means the processor is always given to one of the entities that are present in the ready queue. But what is kept in the ready queue? Processes, of course. If you are not a process, you cannot enter a ready queue, which means you cannot be selected, which means you cannot get the processor. Again, I compact my long explanation into a single sentence. The process is the unit of dispatch. A program has two functions. We do not know if both functions use the same data as input or not. However, we know that the two functions are not dependent upon each other, or the two functions have no data dependency. This means that the output of one function does not become the input to the other function. Conventional compilers run the functions one after the other in the sequence that they are written. So the Python interpreter runs function 1 first and then function 2 later. Concurrent compilers realize that there is no data dependency and can run function 2 after function 1, which is the way sequential execution is done, or function 1 with function 2, which is actually parallel execution. But what we learn from this is, here you are witnessing two flows of execution in this process, or two paths of execution in this process, or two threads in this process. Okay, let us stray a bit from the main topic and talk about something else like concurrency. Let's see what concurrency is. Consider two events A and B. Here I show you 5 scenarios regarding the lifespans of A and B. In case 1, A and B start at the same time and end at the same time. Their lifespans overlap completely. In case 2, A and B have the same starting time, but ending times are different, as B is smaller. In case 3, A and B have the same ending time, but starting times are different. In cases 4 and 5, neither the starting nor the ending times match. Yet, all 5 cases represent concurrent events. So we conclude that two events are concurrent when their lifespans overlap completely or partially. Also, I want to point out that case 1 depicts simultaneous events, that is, events whose lifespans overlap completely. Multi-threading refers to the ability of an operating system to support multiple concurrent paths of execution within a single process. The traditional operating system, which recognizes a single flow of execution in a process, is called a single-threaded operating system. A multi-threaded operating system schedules not processes but the threads that exist within processes. So if there are 2 threads in process A and 3 threads in process B, the multi-threaded operating system recognizes that there are 5 contenders for the processor. Thread 1 of process A, thread 2 of process A, thread 1 of process B, thread 2 of process B, and thread 3 of process B. The dispatcher has not 2 but 5 entities in its queue. I ask you, when the single-threaded operating system assigns the processor, who does it assign it to? And you say, a process. But when I ask you, when the multi-threaded operating system assigns the processor, who does it assign it to? Your answer is different. You say, it's a thread inside a process. And therefore, in a multi-threaded operating system, the thread is the unit of dispatch. An important point to note: in a system that supports threads, the process remains the unit of resource ownership and the unit of protection, but not the unit of dispatch. The one who is allocated memory, I/O, and files is called a process or a task. The one who is selected for execution is called a thread or a lightweight process. So if I am the OS, I give memory to the process. I allocate address space to the process. The program of the process is kept in its address space. Parts of the code of this process, which are self-contained, like functions, are called threads. Where do the threads exist? In the program area of the process image. So this means threads exist inside the process address space. Do you remember that I told you about memory protection? It was something like this. No process can read or write in the OS address space. No process can read or write in another process address space. So when the OS implements protection, it implements it for processes and their address spaces. When two threads are of the same process, they are sharing the address space. So they can read or write anywhere in this address space. But they cannot access memory outside the process which contains them. If two threads belong to two different processes, they can read or write in the address space of the process that contains them, but not beyond the boundaries of this process address space. Here I present you another comic. The address space is like a house, and threads are people sharing this house. The house has been allocated to the process. All threads of the same process share the house. One day, a thread of this process asks for a file. Being the operating system, I get a call from the process that it needs a file. See, I get a call from the process. I make a file handle and place it in the address space of the asking process. I place the file handle in the house shared by threads of the process. Why do I do so? Because the process is the unit of resource ownership. I always give memory, files and IO to a process only. But see what happens. When I place the file handle in the house, all threads of the process can see it. This means that if one thread of a process asks for a resource and the OS grants that resource to the process, placing the handle of the resource in the address space of the process, all threads of a process can access this resource, even though only one of them asked for it. So whatever a process is allocated, it accessible and shared by the threads inside it. Here we look at process thread arrangements, and we can create different operating systems with different process thread arrangements. So we can have a single threaded operating system and we can have multi-threaded operating systems. Let us talk about single threaded operating system. This is an OS that does not recognize a thread. So it knows that there is a process and there is a single flow of execution in that process. There can be two scenarios. You can have an operating system which supports a single user process at a time. Example is MS-DOS. You can have an operating system which supports multiple user processes at the same time. Examples are some variants derived from the operating system that was called Unix. Now let us switch to the multi-threaded operating system. Here the operating system not only recognizes a process, it can identify that there are multiple flows of execution inside a process. Again, there can be two scenarios. You can have an operating system that supports one process at a time, but that one process can have many threads inside it. Example is the Java Runtime Environment or JRE. And finally, you can have an operating system that supports multiple processes and multiple threads within each of these processes. Examples are Windows, Solaris, and many modern versions of Unix. Let us see what are the attributes of a thread, or what are the things that we want to know about a thread. A thread execution state like running or ready. A saved thread context while not running. You must remember context of a process. The context of a process is the values of the processor registers and flags, which are saved when the process is switched out and restored when the process is switched in. The context helps to restart the process from the point where we left execution last time. If we do not save and restore the context, we will start from the beginning every time. Now that the OS is dispatching threads, we are not only going to save and restore the context of the process, we are also going to save and restore the context of the thread inside the process. When I switch out a thread, I save its variable values, stack pointers, flags, so that I can resume this thread from where I left. An execution stack. I told you that stacks are fundamental to function calls and return from those calls. Some per thread static storage for local variables and access to memory and resources of its process shared with all the other threads of this process. In a single threaded system, the process address space has a PCB, a memory area for data and program, shown here as user address space, and stacks for function calls. There always is a stack implemented by the operating system. Additionally, the programmer can also implement a stack. This picture shows both stacks implemented by the user and implemented by the operating system. In the multi-threaded system, there is a PCB for identification of the process. Likewise, there is a TCB or thread control block for identification of each thread of this process. The TCB of a thread contains its context, its priority, its state, etc. Since the threads share the process address space, the user address space is shown in one place. All threads can read or write this user address space. But each thread is a different flow of execution. It will have a different sequence of function calls and returns from these calls. So each thread has its own set of user and kernel stacks. Since this is a new concept, let's pause a bit and see how far we've come. What did we learn so far? Threads of a process share the state and resources of that process. Threads of a process reside in the same address space and have access to the same data. If one thread alters a data piece in the address space of the process, all other threads can see this change. If one thread asks for read privileges on a file, then the operating system grants a file handle to the process with permissions of read access, and all other threads in the process can also read this file. So here we are at the place where I push a question towards you, and as always I'm asking you to pause the video, open a Word document, save it in the format that I've shown you, and write the answer to this question. The book, the William Stallings book, says on page 160, One way to view a thread is an independent program counter operating within a process. Can you explain this to me? So I understood what a thread is, and you've already taught me a chapter on processes. But why should I be interested in a thread? Why? Are there any benefits of threads over processes? And with this question, we look at the key benefits that threads give us over processes. When we create a process, we allocate an address space and we create a PCB. When we create a thread, we create a TCB, which is a much smaller data structure than a PCB. Do we allocate memory to a thread? No. This means thread creation is the time taken to set up the TCB and stacks for the thread. And this means that thread creation time is much smaller than process creation time, which gives me my first benefit. It takes far less time to create a new thread in an existing process than the time it takes to create a new process. When we terminate a process, we deallocate an address space and we delete a PCB. When we terminate a thread, we delete a TCB, which is a much smaller data structure than a PCB. Do we deallocate memory in thread termination? No, we never gave it any memory in the first place. This means thread termination time is the time taken to delete the TCB and stacks for the thread. This means thread termination time is much smaller than process termination time. And this is my second key advantage. It takes far less time to terminate a thread in an existing process than the time it takes to terminate a process. When we switch a process with another on the processor, we transfer control to the OS. The OS changes the processor's mode. Then it saves the context of the process. Then it asks the dispatcher to select a new process. Then it restores the context of the selected process. Then it changes the processor's mode again. Then it transfers control to the selected process. This means that every process switch takes time and requires operating system intervention. Now consider the thread A of a process is running and then it completes. We want to execute thread B of the same process. Do we need to call the operating system to make this switch? No. This is a switch within the same process. No mode switching is required. No need for the dispatcher exists. And the PCB will remain unaltered. Control will transfer from TCB of thread A to TCB of thread B. We conclude that thread switching within a process requires no operating system intervention. And this is the third benefit. It takes far less time to switch between two threads in the same process than the time it takes to switch between two processes. I told you that sometimes one process communicates with another process. But I have also told you that a process cannot access memory outside its address space. The question is, how does a sending process transfer data to a receiving process if both processes cannot access memory outside their address spaces? The answer is simple. The sending process hands over data to the operating system. which writes it in the receiving process address space. So this means inter-process communication needs operating system intervention. But if two threads within the same process need to exchange data, the sending thread can write the data piece in the address space of the process, and the receiving thread can read the data piece, and there is no need to call the operating system. So which communication will be faster? Obviously the one in which no foreign interference is required. The fourth advantage of threads is it takes far less time to communicate between two threads in the same process than the time it takes to communicate between two processes. On page 161, William Stalling writes, if there is an application or function that should be implemented as a set of related units of execution, it is far more efficient to do so as a collection of threads rather than a collection of separate processes. Because threads will be made faster, they will die faster, they will switch faster, and they will communicate faster. If you noted in the previous slides, I was very certain that TCB is a smaller data structure than the PCB. This is the second task for today. How can I be so sure that the size of the TCB is much smaller than the size of the PCB? Class, I have explained what threads are, where they exist, what are their benefits. And now it's time that I give you a few example scenarios where threads are used. So let us first look at the use of threads in a multiprocessor. A multiprocessor obviously is a machine with many processors. And one such use is in the file server. An example of an application that could make use of threads is a file server. As each new file request comes in, a new thread is spawned for the file management program. Because a server will handle many requests, many threads will be created and destroyed in a short period. If the server runs on a multiprocessor computer, then multiple threads within the same process can be executing simultaneously on different processors. See, same process, many threads, and one thread on one processor. Further, because processes or threads in a file server must share file data and therefore coordinate their actions, it is faster to use threads than processes for this coordination. Now you may say, fine, on a multiprocessor machine, you can reap benefits of threads. But what will you do with threads if you have a uniprocessor machine? So let's look at use of threads in a uniprocessor system. I have got multiple examples here. My first example is foreground and background work. In a spreadsheet program, one thread could display menus and read user input, while another thread executes user commands and updates the spreadsheet. This arrangement increases the perceived speed of the application. Perceived speed of the application means the speed of the application as it feels to the user of the application. This arrangement increases the perceived speed of the application by allowing the program to prompt for the next command before the previous command is complete. Another use of threads in a uniprocessor system is something known as asynchronous processing. Asynchronous elements in the program can be implemented as threads. Now you would ask, what do you mean by asynchronous elements? In a synchronous programming model, things happen one at a time. One thing happens, when it completes, then the other thing happens. When you call a function that performs a long running action, it returns only when the action has finished, and it can return the result. This stops your program for the time the action takes. An asynchronous model allows multiple things to happen at the same time. When you start an action, your program continues to run. When the action finishes, the program is informed and gets access to the result. So you start one thing, that thing continues, and the program gives you access to the interface so that you can launch another thing. This is the asynchronous model. Multiple things happen at the same time. So the use of threads can be made for asynchronous processing. As a protection against power failure, one can design a word processor to write its RAM buffer to disk once every minute, auto-saving. A thread can be created whose sole job is periodic backup or auto-saving. The main program can respond to the user without worrying about saving work that has been done so far. Continuing with the use of threads in a uniprocessor system. Threads can be used to increase the speed of execution. A multi-threaded process can compute one batch of data while reading the next batch from a device. What it is doing is that it is using one thread to compute and another thread to read. Even though one thread may be blocked for an I/O operation to read in a batch of data, another thread may be executing, computing result from the batch of data already fetched. Continuing with uses of threads in a uniprocessor system, modular program structure. Programs that are divided into modules or functions. Programs that involve a variety of activities or a variety of input and output may be easier to design and implement using threads, one thread for one activity. Each activity is implemented in a separate thread. This brings modularity to the programs. Modular code is easy to debug and can be readily reused. This means that if you write a thread which does a particular action and later you write another application and you require the same action, you can simply copy and paste that thread from the first piece of code to the second piece of code. So this means that your code is more reusable. Looking at all these examples, we can conclude that multi-threading is beneficial not just when the underlying machine has many processors to distribute the threads to, but even when there is only one processor in the system. Multi-threading is not a concept only for multiple processors. It is a concept that is universal. It is used over uniprocessor systems, used over multiprocessor systems, used over multi-core systems. When we started, we knew what a process is. Now we know what a thread is too. And we know that the thread is beneficial. And we know the exact benefits that the thread provides us. And we have looked at scenarios where the use of threads leads to better applications. Again and again, I ask you to read the book. Read the book. That's very, very important. And keep your task file with you and submit it when I open the assignment in Google Classroom. Write your questions on a piece of paper, Keep it in front of you during the online session. And if you have suggestions relevant to content or quality of this lecture, email them to me. Take care of yourself. And even though this online thing is difficult, please understand that we are in this together. I am learning new things, you are learning new things, and we are going to help each other out of this. Inshallah. Allah Hafiz.